Okay, so I want to graph this rational function, and there are a number of different steps that you need to follow. And I've written them here on the board because I want to try to do as many problems as we possibly can, and I want to follow these different steps. So the first step is to be able to get the function in lowest terms, which it already is, so that's why it's step 0. Step 1 is we want to find the x and y intercept. When we find the y-intercept, we let x be equal to 0. When we find the x-intercept, we let y be equal to 0. So that's the first step that we're going to start with right now. So if we let x be equal to 0, so you're substituting 0 into the function. So in the numerator, we have 0 plus 2 or 2. In the denominator, we have 0 plus 2 is 2. And then we have 0 minus 1 is negative 1. So in the denominator, we're getting a negative 2. So we're getting y is equal to negative 1. That's the y-intercept. The x-intercept, we let y be equal to 0. So that means that the function f of x is equal to 0. Now, if you take the denominator, and in order to clear the denominator, we're going to multiply both sides by the quantity x plus 2 times x minus 1. So now, when I multiply the denominator by 0, now I just have 0 again. So I have 0 equals the numerator. So I have 0 is equal to x squared plus 2. So when I have x squared plus 2, if I was to subtract 2, I have x squared equals a negative 2, which is not going to happen. So that means that there is no x-intercept. That's step 1. Step 2, I want to find the vertical asymptotes. So what I'm going to do is set the denominator equal to 0. So I have in the denominator x plus 2 times x minus 1, set it equal to 0. So I'm getting x equals negative 2 and x equals positive 1 as vertical asymptotes. Then I have step 3. Now, to find the horizontal asymptotes, it's a very simple rule that you follow. And they're here. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. If the degree of the numerator equals the degree of the denominator, then we're going to get a horizontal asymptote equal to the coefficients as a ratio of the numerator and denominator, and I'll explain that. And the degree of the numerator less than the degree of the denominator, we get a horizontal asymptote of y equals 0. So what we're looking at, the numerator is x squared. It has a degree 2. The denominator, if I was to multiply that out, has a degree 2. So now, since the degree of the numerator is equal to the degree of the denominator, we're taking the coefficients of the x squared term, which is 1 in the numerator. The x squared term in the denominator has a coefficient of 1, and the ratio 1 over 1 gives us a horizontal asymptote of y equals 1. Okay, now I want to take a look at long division here. Okay, let's Now, in the denominator, I have x times x is x squared, a positive 2x, and a negative x is positive x minus 2. That's the divisor. And we have x squared plus 0x plus 2. We're going to do long division here. I think I'm actually going to continue this on another page because I don't think I'm going to have enough room. Like that. Okay, x squared goes into x squared once, so we have 1. And then multiply 1 times x squared, 1 times x, 1 times negative 2. And then change the signs of all of the numbers in the second polynomial. So we're getting 1 plus, and then a remainder. Now I can change this around to 4 minus x over our divisor. So what do we have so far here? So we have y equals -1 for a y-intercept. We had no x-intercepts. We had a vertical asymptote of x equals 1 and x equals -2. And we had a horizontal asymptote of y equals 1. Okay, this is what we have so far. So now let's take a look at that remainder that we have. I'm going to call it r of x as the remainder. And we have 4 minus x over, and then we had an x. This was a minus, I'm sorry. So we have an x plus 2 and an x minus 1. So we have different regions that we need to test here as to see what's happening. In the numerator, if I take 4 minus x and I set it equal to 0, I get x is equal to 4. So that's one number that I need to put on the x-axis is a region that I'm going to test. In the denominator, I have a -2 and I have a +1. So that gives me different regions that I need to test here. And I test them into this, into this remainder. So if I pick a number in this region, like let's say I pick x is equal to 5. In the numerator, I have 4 minus 5, which is -1, and then the denominator, I have 7, and then I have 4, so I'm going to end up with a negative in this region. This doesn't make sense. 4 minus 5. I have a -1, and then I have 7 over 4. So this is going to be, something isn't working right here. This is going to be a negative, sorry. This is what I want. Then if I pick a number in this region, let's say I pick 2, I have 4 minus 2, that's positive in the numerator. In the denominator, I have 4 times 1, that's going to be positive, so this region is positive. In this region, if I pick, for example, 0, I have 4 minus 0, which is positive in the numerator. And I have 0 plus 2 is positive, 0 minus 1 is negative, so that's going to give me a negative in this region. And then if I try a number over here, let's say -3, I'm getting 4 minus a -3, which is positive in the numerator. -3 plus 2 is negative, and -3 minus 1 is negative, so that negative times negative is a positive. I'm going to get positive in that region. So what's happening here is I need to take a look at the behavior of this. Since it was an even degree, then we look at the end behavior, and the end behavior is going to tell us what's happening also. So in this region, what I'm going to have is it's going to be positive in this region here. So it's going to stay above the y, the horizontal asymptote y is equal to 1. We're going to stay, it's going to be below here in this region. And then it's going to be positive again up in this region here. So we did the test values to tell us what was happening with the remainder. But when we take a look at the graph, we want to be able to graph it reflective of the vertical and the horizontal asymptotes.